All right. So welcome back to the sixth lecture of this parallel programming class. So today we are going to talk about GPU programming and how we can do GPU computing using CUDA. But this is not going to be an in-depth lecture. So the idea in this part of the course is to familiarize you with CUDA and GPU computing. But I think in period 2, we're going to offer a dedicated course on GPU computing, and then we talk about these things in detail. But in this lecture and the next lecture, we're going to talk about these things quite briefly. Okay. So let's start and let's see why we need GPUs and GPU computing. So we can start from the design approaches in building processors and like computing devices. You can have two types of designs. You can have latency-oriented design and throughput-oriented design. So when you have latency-oriented design, what you care is to is to minimize the latency, right? So you want to minimize the time that it takes to perform a single task. And on the other hand, when you have a throughput-oriented design, you want to maximize the number of tasks that you can perform given a time frame, right? So these are different design approaches for also building processors. So now I have it comes the first question for you. So is the CPU a latency-oriented design? Like, does it have a latency-oriented design or a throughput-oriented design? So what do you think?
Latency-oriented design.
Yes, because we want to minimize the latency, like and the memory bottleneck, right? But on the other hand, the GPUs are designed for having throughput, to maximize the throughput. So we want to perform a lot of operations given a time frame or per second, right? So let's see. So this is the diagram for a CPU that we talked about in the first lecture as well. So you have a big cache that is used to handle latency. You have a few number of ALUs to perform parallel computing, and you have a big control, right? And because you want to have some sophisticated control methods to handle the instruction streams and to remove the latency and things like that. So as you can see, a large portion of the chip is dedicated into cache and control, and you have like relatively a smart part compared to these two for the actual computing. But when it comes to GPUs, you can see that based on this architecture, which is based on this throughput-oriented design, you have a lot of space. So this space that I'm showing. So let me. Okay, you have a lot of space only for computing, right? So you have a lot of ALUs, and you can have a thread for each ALU. So you have a lot of threads, but you don't have a lot of like spaces for cache and for control. So it means the cores in a GPU are simple than a CPU, but you have a lot of cores. That's how you increase the throughput of the computation. So let's compare them a little bit. So on CPUs, you have a few, but probably more powerful ALUs, right? But when it comes to GPUs, you have many, but a small ALUs. So these are like these things comes from the design principle. So you have long latency, but you have high throughput. So that's why when you write applications, you really should consider the hardware that you are developing application for. So if you want high throughput, if you have a lot of computations, mostly you can say data processing computations, you should go for a GPU. But if you have a sequential program, you probably want to do it on a CPU because for sequential programs, CPUs are quite more efficient, right? So as I mentioned, on a CPU chip, you have large caches to avoid the latency, but on GPUs, you have small caches because you dedicated more area on the chip to perform the computations. And on the CPUs, you have sophisticated control like branch prediction or data forwarding when you work with instructions. But when you work with GPUs, you have simple controls because you don't have those things. And more importantly, on the CPUs, you can create a modest number of threads because you don't have a lot of ALUs. But when it comes to GPUs, since you have a lot of computing units or ALUs, you can define a massive number of threads, right? So it really depends on the application that you want to write. So if you have a sequential application and you execute it on a GPU, you probably do not get good speedups, right? And the last thing is on the GPU, you have usually high clock frequency, but on the GPUs, you don't have that. So it means that the cores are weaker on GPUs, but as I mentioned a couple of times, you have a lot of cores. All right. So let's see, well, what is the GPU? I think you already know about that. So GPU stands for graphics processing unit. So this is the GPU, and you can find it on desktop computers as a card, like this one, or on laptops you can find it dedicated on the mainboard. So originally, you would use GPUs for graphics or computer graphics and also for video games, which means you use the GPU for rendering the images or videos or games on your screen. And in that case, you have to process a massive number of pixels on the screen. So that's why in GPUs, you have more ability to do a lot of computations, right? Because you have a lot of data that you want to process and then you want to render on the screen. The GPUs are interesting because you can perform parallel tasks because they are enabling us to perform a lot of computations at the same time. But before 2007, the only way for you to write general purpose programs, not necessarily graphics programs, the only way was to use the GPU APIs like OpenGL and Direct3D. Using OpenGL, for example, you could only use the GPU to program graphics. For example, you want to draw a line or draw a circle or do compute shaders, these kind of things. And any other computations that you wanted to do, like, for example, you can think about matrix multiplication. You should reformulate your problem into something that can be done using these GPU APIs, right? And there's also another API for computer graphics that is called Vulkan. This is relatively new, but you should be aware of that. All right. So it was quite hard to program GPUs for general purpose computations, but using graphics API, like this OpenGL, for example. But it was a good motivation for NVIDIA to develop something called CUDA, which is a programming interface that allows you to perform general purpose computing on GPUs, right? And they did a lot of changes in the GPU hardware and also the software stack to enable developers to use CUDA. So CUDA is a programming interface that you can use. but you have to install it on your system, and it is specific to NVIDIA GPUs. So you need to have an NVIDIA card, right? Then you should install a toolkit called CUDA toolkit. And then in that toolkit, you have CUDA compilers, profilers, and debuggers, and everything that allows you to create programs that can actually run on a GPU. All right. So in this lecture and the next one, we focus on CUDA, and this is the only topic that we are going to talk about GPU computing. But you can also find different GPU programming frameworks. One that I can mention is OpenCL, which is kind of similar to CUDA, but it is multi-platform. So you can use OpenCL on different platforms like NVIDIA GPUs, AMDs, and Apple, and also embedded devices like FPGAs and so on. And there's another GPU programming framework, which is called OpenACC, which is a directive-based programming standard, similar to what you saw in OpenMP, that you can define directives in your C code to parallelize and to send the computations to the GPU. So there are also some, just to make sure that you are aware of, so there are also some CPU parallel programming frameworks like MPI that we are going to talk about, I think, 2 weeks from now, and OpenMP that you already know about. But the important thing here to know is that both MPI and OpenMP can also be used with CUDA. So you can have a distributed memory system consists of different nodes, and in each node you can have different NVIDIA GPUs, and you can program those GPUs using CUDA, and you can manage the nodes and the computations between the nodes using MPI. So we talk about MPIs not in the next lecture, but the one after that. Okay. So let's see how we can do that and what CUDA is used for. So we talked about task parallelism and data parallelism before. So in the task parallelism, as you already know, we decompose the problem into different tasks, right? So for example, here we have task A, task B, and task C. And then these tasks can work with the shared data, set, or with a completely separate data, right? But in data parallelism, what we had was to have a single task or single instruction or single program, like here. We have this single task, and we want to apply it on different pieces of data. So we have, in this diagram, we have task A, and task A is applied on data 1, data 2, and so on. So in these kind of scenarios, you have a huge data set, and you want to process that huge data set in parallel. So what you do is to encapsulate the processing logic in a task and then apply it to each piece of the data in parallel. So this is what data parallelism actually is referred to, right? So when you have a task parallel program, you can assign each task to a thread, right? And then you execute them in parallel. So this is an application that fits quite well on CPUs, right? Because you can have different tasks. But when it comes to data parallelism, you can define a thread for each task, and then you can assign a task to that particular thread, and then you can compute you can execute the thread at the same time. So if you think about GPU architecture, which we are not going to talk about in this class in detail, you see that in GPUs, because you have a lot of threads, but they are designed to compute one like task, like rendering an image to the screen, so similar to that. So this kind of data parallelism architecture is quite fit into the GPU hardware. And for task parallelism, CPUs perform better, right? Because you want to do different things. But when it comes to GPUs, you usually want to do one thing, but on a massive amount of data. So basically, you can have each task on a GPU thread, and then you can work on the data. So just as a takeaway for this slide, GPUs fit to the applications that have a lot of data parallelism, but CPUs, if you want to perform multi-core computing, are fit into applications that use task parallelism. So this is an important concept that you should be aware of. Okay. So let's see a very simple vector addition example and how we can actually do that. So let's think about this sequentially. So we have a vector x, and we have a vector y, and we have an output vector z, and we want to add them, right? So we know that this is a data parallel application because we apply the sum or plus operation on the operands, and they aren't dependent operations, right? So we can apply them one by one in parallel. So it's a data parallel program. But first, let's discuss about the sequential version, and then gradually I will show you how you can implement this algorithm in CUDA and in parallel. So the sequential program is very simple. So we have a vector add function. It receives a pointer to array x, y, and z, and then you have the number of elements as capital M, right? Then you loop through the arrays here, and then you sum them up one by one in this part, and then write the result to the output array Z, right? Very simple. So let's see how we can do that using CUDA, but because I want to show it to you gradually, so we try to build up the concepts on top of each other. So let's first talk about the system organization when you want to write when you want to work with heterogeneous hardware that has both CPU and GPUs on the same machine. And here I'm also trying to show you some terminology. All right, so on a heterogeneous machine, you have a CPU, right? Which is called the host. So whenever in a CUDA program or a GPU program, you saw host, it is referring to the CPU part of the system, right? So you have a CPU, then you have a main memory that is connected with the CPU, and this is called host memory. So the host is your CPU, and the host memory is the CPU memory or the system's main memory, right? That this is it's like a typical machine. But you also have a GPU, which is called the device, right? And your GPU memory, which is called device memory, right? So in GPUs, you have a dedicated on-chip memory, which is called also VRAM, which is used for storing the textures, the frame buffers, and the pixel values and things like that. All right. So in this system, these memories they don't have access to each other's data. So if you want to send some data from the main memory to the GPU memory, you have to do that explicitly. So this is important to know because when it comes to programming that kind of systems, because of these memory boundaries, you should be able, you should make sure that you are sending the data back and forth correctly. And by the way, you should minimize this data transmission. We don't talk about memory optimization of GPUs in this class, but this is something that you should be aware of. So if you want to do some computations on the GPU, you usually have the data on the main memory, right? So you have to send that data to the GPU memory. Do the computation here and send it back to the main memory, right? So I'm going to show you what are the general workflow for that kind of thing. All right. So you have this system, the host and the device, the host memory and the device memory, right? So when you write a program, by default, it is stored in your main memory, right? And everything is in your main memory. So nothing goes to the GPU memory by default. So your program starts with your CPU. So what you need to do in the first step is to allocate some memory on the GPU device, right? Then you transfer, or more accurately, copy the data from the main memory to the GPU memory, right? Then you perform the computations that you want that is parallel or can be parallelized on the GPU. And finally, you return the results from the GPU to the main memory. And after that, you have to deallocate the memory that you allocated on the GPU. So this is a basic workflow when you have a GPU and CPUs on the same machine and you want to program it. So just to emphasize, you have to first allocate the memory on the GPU, copy data from CPU to GPU memory, perform the computations, send the data back or the result back to the main memory, because in GPUs you cannot do the I/O operation. So if you want to print something on the screen, or if you want to write the results to a file, you have to send the data back to the main memory. And then you deallocate the memory that you allocated on your GPU. As you can probably guess, there are a lot of optimizations that you can do here. So you can reduce probably this transfer because they are time consuming. And one other optimization that you can do is to keep the data in the GPU memory as much as possible to reuse. But we are not going to talk about these things. So the only thing that you should understand so far is this workflow that I just explained. Okay. So this is how you perform these computations, but let's talk a little bit about the memory management API that CUDA provides for you. So how we can do these things in actual code. So in CUDA, you have different functions that you can use. For allocating memory, you can use this CUDA malloc function, which is very similar to standard C malloc function, which is used for allocating memory. And for that, you need to send an address of a pointer on the GPU to this function, and also the number of bytes that you want to allocate, right? We will see some examples on this. And for memory deallocation, you have CUDA free, not like free like in C. So as you can see here, these APIs are quite similar to the APIs that the C language provides. And that's why I mentioned in the assignments that you should manage memory without C++ advanced features like smart pointers. Because when it comes to GPU computing and CUDA, what you do is to manage the memory quite manually, similar to what you do in plain C code. All right. And all of these APIs return a CUDA error type that you can check for errors and if something is is wrong in the calculations. Right. And for copying data from one memory to another, you can use this CUDA mem CPY or CUDA memory copy. It receives some arguments, the address of the destination pointer, destination like array or data, the address of the source data, the number of bytes that you want to transfer, and then the type of the transfer. And you can have different type of transfers, like host to host, host to device, device to host, and device to device. And between all of these four, this host to device and device to host, these two are the most important ones. Okay, so let's see an example how we can do that. So this is the original vector add function that we had, right? Which was sequential, but now we want to make it a parallel function. So within this function, as I mentioned, in the first step, I need to allocate some GPU memory. So I define 3 pointers, one for X, using this X underline D, and D stands for the device. If you want to allocate some memory on the host, you should name it as like the name underscore H, and H stands for the host. All right. So we allocate some memory for, we first define the pointer on X, Y, and Z, right, on the device. And then we use this CUDA malloc to allocate memory on the device. So this CUDA malloc, when you use it, you should also cast the address of your pointer into void star star to make it generic. So it's how this CUDA malloc receives this pointer. And then you specify the number of bytes that you want to allocate. In this case, we are working with floats, so that's why we use this size of floats. Then you allocate memory for Y and for Z, right? So far, we have some memory allocations on the GPU memory. Now we have to copy the data from the host memory, like this X, Y, and Z. We have to copy them to the GPU memory, right? And for that, we can use CUDA mem CPY. So first, we send the destination address, XD here, then the source and the number of bytes, and the type of the transfer, which is host to device, right? CUDA mem CPY host to device. And we do the same thing for the next array, right? All right, so now I have a question for you. Should I also copy the data of Z to the device, or it's not needed? Any ideas?
It's not needed.
Okay, why it is not needed?
I think when you use the CUDA malloc, it was automatically transferred
Well,
to the GPU.
everything is done explicitly, so nothing happens automatically, right? So we send the data of X and Y to the GPU device, right, using these two lines, but we didn't send the data of Z to the GPU device. So the question is, why we didn't do that?
Because it's an array for the answers.
Yes. So because we want to store the answers here, so we don't need to send the data of this Z to the GPU. We do the computations on the GPU, right? And then we send the result from the GPU to this array. So here we copy the data from the host to the device. We do the computations here on the GPU that we're going to talk about later. And then after the computation is done, you have this ZD with the results, and then you copy the content of ZD to the host memory using this Z array. And for that, you should use this CUDA memcpy device to host, because we are sending the data from the device to the host, right? And finally, you have to free the memories that you allocated using this CUDA free. Okay. So the only part that we didn't talk about is how to perform the computations on the GPU. So far, we just talked about the memory management on the GPU, and for that, you should know for computing, for the actual computing on the GPU, you should know about the way that CUDA structures the threads and how you can use that structure to do the actual computation. Okay, so far we had this program, this problem. So we have vector x, vector y, and vector z. So what we want to do is to assign a thread to each of these elements in x, y, and z, and then do the summation. So each thread will be assigned to each data element, right? So for that, assume the lengths of our arrays are n. We want to have roughly n threads. Okay, well, let's see how we can do that. So this is the number of threads that we want. So in CUDA, an array of threads is called a grid, right? So you have a grid of threads, and a grid is further decomposed into something called thread blocks. So so accurately, a grid is a set of thread blocks, right? So I have 4 thread blocks here, and each thread block has like 4 threads in it, right? And here I have a one-dimensional grid along the x-axis. So if this is my axis, x, so this is called one-dimensional grid. I can have up to 3 dimensions. So I can have another axis called y, and another one called z, and then I can have a cube of thread blocks, and each one has different threads in them, right? And each block can also have 3 dimensions. So in this case, we are having only 1 dimension for the grid itself and for the block, right? So if we have 2 dimensions for the blocks, we probably have something like this. Thread, we have threads here, so on. We will talk about that later. But the important thing to know in this slide is that the threads are organized into blocks, and the blocks are organized in a grid. So you have a grid of thread blocks, and each thread block has different threads, and they can be up to 3 dimensions. Okay, so when you want to perform the computation on the GPU, what CUDA does for you is to launch a grid of threads, right? It launches a grid of threads, and then it's your responsibility to manage those threads and to coordinate them to solve your problem on the GPU. So for that to happen, you should define a function which is similar to the C function called a kernel. And this kernel function, as I said, which is a typical C or C++ function, is executed by all the threads within this grid of threads, right? So you define an appropriate block size and the grid size, and then you define a kernel function, and then this kernel function is executed on all threads that you define. So for example, here I consider 512 threads per block, right? And then I divide the number of elements that I have, this n, by the number of threads per block, and this gives me the number of blocks, right? And by the way, everything here is 1D, because we are talking about that vector addition problem. And then you can launch a kernel. Let me erase this thing here. Just give me a second. Anyway, doesn't remove. So you can you can launch a kernel with this syntax. So let me explain what it is. So this is the kernel name, a typical C++ like name for the function. And this is the list of function arguments, right? So in CUDA, you have this syntax with these three braces here. And within these braces, you specify the number of blocks and the number of threads per block. So for example, if the number of blocks is 2 and the number of threads per block is, I don't know, 16, then you are launching a grid, right? You launch a grid of 2 blocks, right? We have 2 blocks, and each block has 16 threads in it. Okay? And when you launch this kernel, all of the threads in these blocks, basically the whole grid, will execute this kernel. And within that kernel, you manage a parallelism. And everything is done explicitly. So let's see how we can do that. So as I mentioned, a kernel is a typical C++ function. To specify that your function, that your C or C++ function is a kernel, you have to annotate that function using a keyword called global. So when you have this global keyword before the function definition, the compiler knows that this function is a kernel, and it should launch a grid of threads for this function, right? You can also have different keywords that you're going to be familiar with. All right. So now that we know how to launch a kernel and how to define a grid, we need to access the information of this grid within the kernel. And we need this information because we want to assign different tasks to each thread. So let's see what CUDA provides for us within the kernel. So the first thing that you can get is the dimension of the grid along the axis, right? So for example, here we have a one-dimensional grid, right? Along axis X. So if you want to know how many blocks are in the grid, you can use this grid dim.x. It gives you the number of blocks in the grid along the X axis, right? So the next piece of information that CUDA gives you within your kernel is the indices of the blocks. So for example, in this case, we have 4 blocks. So we can have each block has its own index. So this is block 0, block 1, block 2, and block 3. And still, because a grid can be multidimensional, you should also get the block indices along the direction that you want. So in this case, we are getting the index of the block along the x direction, right? So we want using that we can identify the position of the block in the grid. And then similar to grid dim variable, you have this block dim variable, which gives you the number of threads in the block along the x direction. So if you use block dim -y, it gives you the number of threads along the y direction. And similar to block indices, we also have thread indices. So within each block, we have an index for the thread. So this is index 1, 0, 1, 2, and 3. This is also 0, 1, 2, and 3. Okay. So as you can see here, the threads, they have local indices, right? So this thread is the second thread in the block, but it's not in the it's not the second thread in the grid. So you should be able to compute the global index for the thread as well to make sure that your thread is working on the piece of data that you want that thread to work on. We'll see that in the next slides. Okay, so let's get back to our example. So we had this input vector x, input vector y, and now we launch a grid of threads, right? Or more accurately, grid of thread blocks. So we launched 4 blocks. Basically, we have 16 elements here. This is 16. And we launched 4 blocks, and each block contains 4 threads, right? So basically, we have 16 threads. And you should know that the number of threads in each block is the same as the number of blocks threads in other blocks. So the number of threads in a block is fixed for all blocks. So you cannot really have 4 threads in this block and 2 threads in this block, right? This is how CUDA works. Okay, so now let's write a very simple kernel to perform this vector addition calculation in parallel. So let's see how we can do that. So as I mentioned, a kernel is a typical C function. So here we named it vec_add kernel, right? And a kernel should return void, basically should return nothing. And we annotated this function using this global keyword. So now the CUDA compiler knows that this function is not a typical C function, but it's a kernel that should be executed on the GPU threads. So what I want to do as a logic here, I want one thread 0 basically, works on the first element, thread 1 works on the second element here, thread 3 work on work in this element, and so on. So the only thing that I need to get is the global thread index. So for example, this thread should work on this element, right? So this thread, the thread ID here is 0, 1, 2. The thread index is 2. The block index is 0, 1, 2, right? And we know that within each block, we have 4 threads. So then using this simple line, I can compute the thread global index within the x-axis. So I just need to multiply the dimension of the blocks with along the x direction. I have to multiply this with the block index, and then I have to add an offset using this thread index, right? So in this case, the last thread here has the index of 3, but when you compute it here, it has access to the 15th element of this array, right? So this way I can completely get rid of the for loop. And now if you think about it, the whole vec_add function is launched. The whole function is executed in all of these threads. So all of these threads have access to this function. So then each thread identifies the index of the array that it needs to work on using this I. Then it only manipulate that portion of the arrays. So it just sums the xi plus yi and then writes it to the zi. Only one element. But since all of these threads are performing the exact same computation, so we don't need a for here. So everything is done in parallel. Okay, any questions about this kernel? All right. But there's a catch here. As I said, here we have 16 elements, and we could define 16 threads. And we have a limitation in CUDA because we have a limitation in CUDA, which is the number of threads in all the blocks should be the same. So assume we had 17 elements, right? So in this case, I needed to create another block as well. So in that case, I had 5 blocks and totally 20 threads, right? And in this case, I have 3 threads more that they should not do anything, right? So then I have to, for doing that, I have to check some boundary conditions here. And this is what I want to talk about. So as I mentioned, if the number of elements is not a multiple of the number of threads per block, you usually have fewer threads, right? So in this case, you just round this division up, right? Then you have another block, and then by introducing a new block, you have a set of new threads, and then you have to manage those threads as well. So it's quite easy to handle. So in this case, we have 14 elements in our arrays, and we defined 16 threads. So I have to provide a simple if condition and just make sure that these 2 threads that are redundant ignore the computation. So we can do it like that. So as before, I have to calculate this global thread index to know on which data point exactly my thread is working. And then we check the boundary condition here. So if this index is smaller than n, the number of elements, we do the computations. Otherwise, we do nothing. So in this case, those threads that are redundant, they just ignore this calculation. All right. So this was about writing these kernels and launching them. So let's see how we can compile it. I will also try to show you a live demo for this example as well. All right. So what you usually do when you want to develop a CUDA program, in the simplest case, you create a .cu file or cu files, right? And you can write C, C++, and CUDA code here. Then, after you've developed your program, what you do is to use this NVIDIA CUDA compiler or NVCC, which is installed when you install your CUDA toolkit. So you use this NVCC to compile this .co file, and NVCC decomposes your code into the pieces that are in pure C and C++, right? So here, if you have a pure C code or the host code, the compiler sends it to a typical C++ compiler that you have on your system, and then it generates the assembly and finally the binary, executable binary that is run on the CPU, right? Then it compiles the CUDA part of your code into a parallel thread execution file or PTX file, which is a virtual binary file that provides an abstraction to make sure that your code works on different GPU architecture. So it's a assembly-like code that NVCC generates for you, and then it compiles this .ptx file into the actual binary that is run on your GPU, right? So this is how you compile your CUDA programs. So before continuing in the lectures, in the slides, let me show you a short demo and the full program for this vector addition. So give me a second. Right. Okay, so let me share. All right, can you see my VS Code window?
Yes.
Okay, is it visible? Can you read the text?
Yes.
Okay. So I set up the environment using my CMake. So here I just try to explain the CMake file a little bit. So I think you are already familiar with that. So here I just specify the minimum like version of CMake. Then you have to specify the CUDA architecture that you want to use. So it depends on your GPU. Then you define your project. So in my case, I called it CUDA apps. Then you specify the languages that you want to use in this project. So in this case, I use C++ and CUDA. Then you specify the C++ standard, which is in this case 17. Then you make them compulsory here. Then if you have CUDA installed on your machine, you can use this find package to find the CUDA library and its header files here. Then you can check if it is found correctly. So this is for OpenCV, which I'm going to talk about later. Then, for example, for my vector addition example, I add an executable called vector add, and then I have this vector add.cu that implements this vector addition, and then I have to link the CUDA library to my executable. So for the vector addition, that's the line responsible for that. So here I'm linking the CUDA runtime library with my vector addition file, CUDA file, right? So it should be quite clear. So this is the whole the entire file. So let me explain what it is. So this is the kernel that I was talking about, and make sure that you include this CUDA runtime header file before you write anything. So you can define this global here, or I think you can also annotate it like that as well. Then, so this is my vector addition kernel. So these are my arrays, and this is basically what I explained in the slides, right? So let's see how we can define other things. So this is my main function. I just define the number of elements that I want to add. Then this is the size, the number of bytes that I need to store these elements, right? 1 million elements. Then I allocate some memory in the host, right? HA, HB, and HC. A and B and C arrays using normal malloc function, because I first need to like allocate memory on the host, and then initialize them to have the data, and then send it to the device. So we assume that the data is already available on your host memory, right? Then I initialize the vectors with 1 and 2, right? So I want just to have the result would be 3 in this case. So now I want to offload the computation on the GPU. So what I need to do is to allocate some memory on the device or the GPU. So I define 3 pointers, DA, DB, and DC. Then I allocate some memory using these pointers on the device using this CUDA malloc function. By the way, you don't need to do this part. And then I need to copy the data from the host to the device, right? Using this CUDA memcopy. So I send HA, or the array A, which is stored in the host, to this to the device, and using this host to device transfer type. And then I send HB to the device as well from the host using these two. So now that my data is on the GPU memory, so I can launch the kernel. So as I showed you, I defined the kernel here. So the first thing that I need to do is to calculate the number of blocks and the number of threads in the block. So I just considered 256 for the block size, and make sure that this number is it should be a multiple of 32, and like it cannot be more than 124. So these things are they depend on the architecture, hardware architecture of the GPU. We're not going to talk about that, but you cannot have more than 1024 threads in a block, and the number of threads in a block should be a multiple of 32. And this is the maximum. All right, then I define the number of blocks using the number of elements and the block size, and then using this syntax, I can launch my kernel, right? So I launch this vector addition kernel, then I specify the number of blocks and the block size, and then I pass in the arrays that are sitting on the GPU memory. After this kernel launch, if everything works correctly within the kernel, I have the results in this DC, in the C array, and this result lives in the GPU, on the GPU memory. So I have to send it back to the CPU for I/O operations, for printing and things like that. And I again use this CUDA memcopy. So I have this DC as a source array and then HC as the destination array. And here I use the device to host, not host to device. In this case, I use because I want to send data from the device to the host. And now I'm able to print, for example, the results here. And after that, I need to free the memory that I allocated on the device using this CUDA free, and then on the host using the typical free. Then it's optional, but you can reset your CUDA device because CUDA also allocates some internal memories for its internal computation. You can also deallocate them as well. All right, so let's see how we can compile this code. So I can show you the compilation. Let me zoom in here a bit. So make sure that you have this NVCC, the CUDA compiler installed on your machine if you have NVIDIA cards. But by the way, on the next Wednesday, next week, I'm going to have a workshop in Turku, and I will show you how you can access these NVIDIA GPUs available on this CSC supercomputer. So you can remotely have access to NVIDIA GPUs there, and you can do your assignments and project also there as well. So, but if you have an NVIDIA GPU on your local machine, you have to install CUDA toolkit. Probably I can talk about that later as well. And then finally, you will have this NVCC compiler available on your system. But I don't use NVCC directly because I compiled my code using this build system CMake. And for that, I just need to navigate to the build folder that you can create. Then you call CMake. Then it sets up the compiler for you, and then you can call this the make function to compile the actual code. So here, I can run this program like add, and this is the result. For example, I have printed the first 5 elements of in the resulting vector, which is 3. So 1 plus 2 is 3. All right, so this is the typical workflow when you want to write a CUDA program. All right, so let's get back to the slides. All right, can you see the slides?
A white page, but yeah.
Sorry?
I see a white page, but
Yeah, it is. Yeah, it's a blank page, yes. All right. So we talked about the compilation. So there are other keywords for function declarations in CUDA other than this global. So let's first talk about the global, and then we talk about the others. So the global keyword that you use to annotate your functions, as I mentioned, identifies the kernels, right? So the kernels execute on the device, right? But you can call them from the host and recently from the device. But originally, you could define the kernel that is executed on the device, but it is called from the host, right? So this is used for defining the kernels. Kernel. Sorry for my bad handwriting. All right. So you can also have a host keyword that you can use for annotating your functions. And the functions that are annotated with the host keyword, they can be called from the host, and they execute from the host on the host, right? So they are typical C++ functions. So completely the same thing. So they are called from the host and they execute on the host, right? And then you can also have this device keyword. And the functions that are annotated using this device keyword, they are called from the device and they execute on the device. Okay. So, but there is some catches here. So, for example, here when you call this function that is annotated with the global, which is a kernel, in this case you launch a grid of threads. But when you have the function with this device keyword, you do not launch a grid of threads. It means that one of the threads or all of them, depending on your code, can execute this function as a normal function on the GPU. So when you annotate your code, your functions in your code with these keywords, the CUDA compiler knows which function is going to be compiled for which piece of hardware. So now there's the question. So if host is used for normal C++ function, and it is a default behavior, so why we really need this host keyword in our code? So why should we have this? Anyone has any ideas about this?
I think maybe for cleanliness of the code.
For what?
Cleanliness of the code.
Well,
Readability.
yeah, it can be for that as well, but there is another reason.
Maybe you want to restrict one function to just execute on the CPU.
Well, by default, your functions are executed on the CPU. So this is the defined behavior of CUDA.
Yeah, but I just meant like we want like there is a function with like sequential nature, and we don't want it at any point to be like. Yeah. Anyway, I
Yeah,
just
well,
guessed that.
yeah, that also could be true, but the main reason to have this host keyword is when you want to define a function that are executed. If you want to define a function that is executed on both CPU and GPU, right? So if you want to have your function compiled for both CPU and the GPU, so you should use this host with the device, because if you use the device by itself, it is compiled on the GPU, and if you do not use anything, or if you use host, it is compiled to work on the CPU. But if you want your function to work on both devices, then you should have the host and also the device together. So you can see it as an example here. So this function is annotated with the host keyword, right? So it is run on the CPU. Here we didn't annotate the function. So by default, again, it is run on the CPU. But here we have a global, so it launches a kernel, right? All right. So make sure that in your code you define these keywords correctly, otherwise the compiler may be confused when it wants to compile your code. All right. So something important about these kernel executions is that by default they are asynchronous. So it means the CPU portion of your code does not wait for the GPU to finish the computation. So in this case, you can have overlapping computations between the CPU and the GPU. So it again depends on your application, but if you want to perform device synchronization, if you want your CPU waits until the GPU computation is done, then you should use this CUDA device synchronize function that is available in CUDA runtime header file. In this case, your CPU computation is blocked until the GPU computation is finished. Okay, and some small points about the error checking. So here, always similar to the C code, make sure that the CUDA functions like the CUDA malloc, CUDA free, and like this device synchronization, everything. Just to make sure that these things are working properly, you should always check for the errors using this CUDA error T type, right? And then you check with this CUDA success, which is also available in CUDA runtime, QRT. And then you can get the string version of the error using this CUDA get error string. So typically, this is how you check for errors when you call any API functions from the CUDA runtime library, right? However, this thing only works on the CPU side because you allocate, for example, considering CUDA malloc, it is your CPU that requests for memory allocation on the device. But sometimes you might have some errors within your kernels or within like that this CUDA device synchronize function or something like that. So in this case, you should get the error using this CUDA get last error function, right? So let me explain a very difficult to catch, but a typical case. So when you write, let me show it to you probably. Let me share my screen again. All right, can you see my window again, my VS Code?
Yes.
Okay, so I'm just working with the terminal, so you don't need to look at the code. But when you have an NVIDIA driver installed, you can have this NVIDIA SMI command, which gives you some information about your GPU, right? So in this case, I have an GeForce RTX 4070 GPU with this information, but there is a quite important thing here in this NVIDIA SMI report, which is the CUDA version. And you have the driver version as well, right? So these two are quite important because it tells you that for this specific NVIDIA driver version, right, the CUDA version that you should install is this version. So for this version, I need to install CUDA 12.2. So if I install another version of CUDA, it does not work with this NVIDIA driver, right? But assume you didn't know about this and you installed an arbitrary CUDA version with an arbitrary driver version. So in this case, your code completely works. You never get an error. So you're not going to be aware of this problem. But the problem is when you launch your kernel, you still don't get any error, but the computations, the result of the computation will be wrong. And you should kind of understand it if you understand the logic. So for example, in this case, 1 plus 2 might be 1, right? But this is a very simple case that you can really understand. But in some more complicated scenarios, your kernel will fail and the CUDA library doesn't tell you what is the problem, right? So if you use this CUDA get last error, so here after I launch my kernel, I can have this error checking like CUDA get last error, right? So in this case, I use this, and then I get this CUDA error t as my error. Sorry. So I have this CUDA error t as my error, and then this error gives me enough information about what's happening between my kernel, right? So this is one of the use cases that this CUDA last error might be quite useful. So when you have, then you see that, okay, apparently the CUDA version and the driver version, they don't match. So then you should install the proper CUDA version, and you can get different kind of problems within your kernel launch. And you should be aware of these errors using this CUDA get last error. So always make sure in your CUDA programs, you use this CUDA get last error function after the kernel launch. If you have multiple kernel launches, then you can have multiple CUDA get last error function calls. So this is something very important that you should know. All right, so I think this is what I wanted to cover for today. So we can also talk about the multidimensional data, but I think it takes more time, so probably it's better to have it in the next lecture. All right, so is there any question?
I actually wanted to ask about multidimensional data, but yeah,
Okay.
maybe next time.
Yeah. For next time, we talk about multidimensional data and how to process images, how to write kernels for images, and we are going to implement two applications for image processing. One of them is image blurring application, and another one is an application that you like have this have a color image and then you want to make it black and white or gray style image. Yes.
I think my question maybe will be different. So I don't understand why do we have multidimensionality from the CUDA level? Because from a hardware perspective, it's just 1D. And I can do the multidimensionality using regular C syntax. So why do I have this CUDA multi-layer grid thing?
Yes. CUDA is used for data parallel applications, right? So when you have data parallel applications, it means that you have a lot of data to work with. And that data can have its own structure. So you can have 1D data, you can have 2D data, you can have 3D data and more, right? So what CUDA provides for you, for the programmer, is to allow the programmer to structure the threads aligned to the structure of the data. So if you are working with a matrix, right, with the matrix multiplication, because so matrices are 2D arrays, right? Then you can structure your CUDA threads also in 2D arrays. So in this case, it is quite easier for the programmer to assign different tasks to the threads of the CUDA grid. So in this case, the main idea for this multidimensionality in CUDA is to align your threads with the data structures. So this is the main reason.
But there is no like advantage in performance. It's just ease of coding.
It just helps you to better divide the workload between the threads.
Yeah, because we can still do that with the C syntax.
Yes. Yeah, in this case you have easy like indexing. You can know exactly what thread is working on what, and it's quite simpler to work with. Yes.
Okay, thank you.
You're welcome. All right, any other questions? All right, so next time we talk about multidimensional data, how we can write CUDA kernels for image processing applications. All right, and thank you for your presence, and have a good week, and see you next time.